Howdy, welcome to Math 153, Elementary Statistics. I am Lance Curtis, and this is the lecture for Section 8.3. You can see Section 8.3, testing a claim about a proportion. So now that we've gone over the basics of hypothesis testing, we're going to talk specifically about testing claims made about proportions. Key concepts for this section. As I mentioned, we're going to examine procedures for testing hypotheses or claims made about a population proportion. To do this, we'll use the p-value or the critical value, as we learned in the previous section, but we're also going to add on use of confidence intervals to perform hypothesis testing. We're also going to look at two common methods or approaches, really, for testing a claim about a population proportion. The first is using a normal distribution to approximate the binomial distribution. This is what we've been doing all along. So, in the testing of hypotheses made about population proportions from the last section, this is in effect what we were doing, using the normal distribution as an approximation to the binomial. However, we could actually skip using the normal distribution to approximate and just go directly to the binomial distribution itself if we wanted a more exact method. We'll get to that later in the lecture. First, since we are generally using the normal distribution to approximate the binomial, three requirements need to be met when we're testing claims about population proportions. The first is that the sample observations are produced from a simple random sample. Next, we need to know that the conditions for the binomial distribution are satisfied. This allows us to use the binomial distribution. What allows us to use the normal distribution to approximate the binomial is the conditions that NP, or the number of successes, is at least 5, and NQ, the number of failures, is at least 5. Once we have those three requirements met, then we're set to go. Now, please note that lowercase letter p is the assumed proportion in the population, and not the sample proportion. Typically, we've used lowercase letters to represent the sample statistic, and the population parameter is indicated with a capital letter P. But in this case, we use the lowercase letter p to represent the proportion because the uppercase letter p is used to represent probability. Therefore, the sample proportion is designated with p hat. Let's take a look at our test statistic. So, since we are using the normal distribution to approximate the binomial, our test statistic is a z-score. And that's the first thing we need to notice about the test statistic, that it is an actual z-score. Next, p hat, as I just mentioned, is the sample proportion. So we take the number of successes, if you will, divided by the sample size, and that gives us p hat. P itself is the population proportion. This is the proportion that's contained within the claim. The claim is always about the proportion, so we're going to take p from the claim itself. Q is the complement of p, so whatever p is, we just subtract it from 1, and that gives us q. And n, of course, is the sample size. Now that we're clear on the test statistic, we need to understand different ways in which we can decide the hypothesis test. And there's 2 or 3 ways we can go about it. The first is comparing the test statistic with the critical value. Second, we could compare the p-value with the significance level alpha. These are the 2 methods that we saw previously in Section 8.2, and they are based on the use of the normal distribution as an approximation to the binomial. If we have a two-tailed test, there's a third option that we have, and that is to construct a confidence interval at the 1 minus alpha confidence level. Why is this option available only for two-tailed tests? Well, because every confidence interval has 2 bounds, a lower bound and an upper bound. just as every two-tailed test has two critical values. A critical value bounding the lower tail of the distribution and a critical value bounding the upper tail of the distribution. So for this reason, because the only way you can get it to match up is if you have a two-tailed test, the option to use the confidence interval is available only with two-tailed test. When testing claims about a population proportion, using the test statistic or the p-value are equivalent and will yield the same result since they both use the same standard deviation based on the claim proportion p. However, if we use the confidence interval, okay, it's going to use an estimated standard deviation that's based on the sample proportion p hat. And because of this difference, there is a possibility that the confidence interval could yield a different conclusion than the test statistic or the p-value. This is particularly true when you're trying to use a confidence interval with a one-tailed test. However, you could also see it with a two-tailed test. So, because it's based on a different standard deviation, you could see a different result coming out of using that decision method for your hypothesis test. And because of that, best practice is to use the confidence interval to provide an estimate of the population proportion. So we use the confidence interval to estimate the parameter, but then when we're going to test a claim about the proportion, we're going to use the test statistic or the p-value. Here's an example to illustrate antivirus programs. So, National Cybersecurity Alliance reports that 93% of computer owners believe they have antivirus programs installed on their computers. But in a random sample of 400 scanned computers, 380 of them actually have antivirus software programs. So 380 out of 400 is 95%. We can use the sample data to test the claim that 93% of the computers have antivirus software. First, let's check to make sure our requirements are met. First requirement is that the sample observations come from a simple random sample. In this case, they appear to be. The conditions for the binomial distribution are satisfied. So each of the trials are independent. Each of the trials has only one of two outcomes, success or failure. And we have the conditions for the binomial distribution satisfied. We also have at least 5 successes and 5 failures. So 93% have the computer antivirus program installed, whereas 7%, which is 28, do not. So that requirement's met. This allows us to use the normal distribution as an approximate for the binomial. We're now ready to conduct our hypothesis test. So the original claim is that 93% of the computers have antivirus software. We can express this as P equals 0.93. Our null hypothesis is then P equals 0.93, because remember, the null hypothesis is, by definition, a statement of equality. So if our claim is that P equals 0.93, that has to go with the null hypothesis. The alternative hypothesis would then be P is not equal to 0.93. Now notice that what we have here, because we're using the not equal in our alternative hypothesis, what we have here is a two-tailed test, because we're using the not equal sign in our alternative hypothesis. So for a significance level, let's select alpha equals 5%. That's the most commonly selected significance level, so we'll just take that as our alpha. The relevant sample statistic is p hat, and our test statistic, as we saw earlier, we can calculate that, and out comes 1.57. So z equals 1.57 is our test statistic. We're now ready to decide our hypothesis test. There's different ways we could go about it. Let's start by looking at the p-value method. So we're going to use the p-value to determine our two-tailed hypothesis test with a test statistic of z equals 1.57. So the p-value we're looking for, because it's two-tailed, we want twice the area in one of the tails. So our test statistic 1.57 is bounding the right tail. So we're going to find the area in that right tail and then take twice that area. That gives us our p-value, 0.1164. Alternatively, we could take the area in between the two tails, subtract it from 1, and that gives us the area of both tails itself. And you can see, if we follow this methodology, we get the same value, 0.1164. So our p-value is 0.1164. We now compare this value with our confidence, or excuse me, our significance level, alpha, and we find that 0.1164 is greater than 0.05, so therefore we are outside the critical region and we fail to reject H0. If we use the critical value to conduct our hypothesis test, again, two-tailed hypothesis test with a test statistic of z equals 1.57. So we have a two-tailed test. We have two critical values, one for each tail. And you could see them here on the screen, negative 1.96 and 1.96. These are our critical values. We then look at our test statistic and compare it with the critical values. Where does it lie with respect to the critical values? Well, our test statistic lies just to the left of the rightmost critical value. We're here in the region of failing to reject H0 because the critical region, which is the tails, is where we would reject the null hypothesis. We're not in the critical region. We are outside the critical region in the center part of the distribution. So therefore, we're going to fail to reject H0. If we use the confidence interval method, so we have a two-tailed test, so we could actually use the confidence interval method if we like. Our alpha level is 5%, so that corresponds with a 95% confidence level. So the first step in constructing our confidence interval is to calculate the margin of error. You may remember this little equation. We're going to use it to calculate margin of error. So we plug in what we know. There's our critical value, 1.96. P hat is 95%. That's from our sample. Q hat, also from the sample, complement of P hat, 5. And then sample size of 400. Punch that out on your calculator, and out comes 0.021. So now we write the general form of our confidence interval, and we plug in what we know. So P hat is 95%, and we're going to subtract the margin of error on the left, 0.021, and add it on the right. And when we do that, we get bounds of 0.929 and 0.971. So our claimed population proportion of 93% is within the confidence interval. That means that we're going to accept the claim, which is the equivalent in hypothesis testing of rejecting H0. Well, notice that rejecting H0 is a different conclusion than what we produced when we used the p-value or the critical value. In those instances, we failed to reject H0. So here we have an instance where the confidence interval is producing a different conclusion than the p-value or the critical value. And for this reason, the best practice is to use the confidence interval to estimate your population parameter, and then to use the p-value or the critical value to test a claim or a hypothesis made about that population parameter. So our final conclusion we'll take from the p-value and the critical value. There is not sufficient evidence because we failed to reject H0. There is not sufficient evidence to warrant the claim that 93% of computer owners have antivirus software. If we want to go with the more exact method of hypothesis testing, then we're not going to use the normal distribution to approximate the binomial, which is what we've been doing up to this point. We can just discard all of that and go straight to using the binomial distribution. Well, because we're not using the normal distribution as an approximate, we no longer need to check that we have at least 5 successes and 5 failures in our sample. That was simply a requirement that allowed us to use the normal to approximate the binomial. Since we're not going to do that, we don't need to check for that requirement if we use the binomial distribution directly. So how do we decide our hypothesis test? Well, if it's a left-tailed test, the p-value that we're going to use is the probability of getting X or fewer successes among n trials. If we have a right-tailed test, the p-value is the probability of getting X or more successes among n trials. And for a two-tailed test, we have to compare the sample proportion with the population proportion. If the sample proportion is greater than the claimed population proportion, then the p-value we're looking for is twice the probability of getting X or more successes. We just take that rightmost tail and we get twice that to get our p-value for a two-tailed test. If, on the other hand, our sample proportion is less than our claimed population proportion, then the p-value we want is twice the probability of getting X or fewer successes. So we're going to take that left tail and we're going to double it so that we get our p-value. Let's look at an example of how we might apply that. So in testing a method of gender selection, 10 randomly selected couples are treated with the method. 9 of the babies are girls. So of the 10 couples, 10 births, 9 of the births are girls, which means only one was a boy. So use a 5% significance level to test the claim that with this method, the probability of having a baby girl is greater than 75%. So what's our null and alternative hypothesis? Well, from the claim, the null hypothesis is always a statement of equality, so p equals 0.75. That's the percentage that comes from our claim. The alternative hypothesis is directly from the claim itself. There's no statement of equality with the claim, so we just take the claim itself and reflect it in the alternative hypothesis. So, look at the alternative hypothesis. It's greater than. That inequality sign is like an arrowhead pointing to the right. We have a right-tailed test. And because we have a right-tailed test, the p-value we want is the probability of 9 or more successes among the 10 trials, assuming that the probability of success is 75%, as was claimed. So, if we create our binomial distribution with those parameters, we find that our p-value is 0.2440, which we compare with alpha. Notice we just take the area in the one tail because it's a right-tailed test. If it were a two-tailed test, we would need to double that area to get the p-value. But because it's a one-tailed test, there on the right, we just take the area under the one tail. That is our p-value. Now to finish our hypothesis test, we compare the p-value with our significance level alpha, and we find that 0.244 is greater than 0.05. Therefore, we fail to reject H0. And conclude there is not sufficient evidence to support the claim that the probability of having a girl is greater than 75% with this gender selection method. That brings us to the end of this lecture. If you have any questions, you know how to get a hold of me. Otherwise, I will see you in class. Thanks for watching.